Okay, hello class. Again, I want to apologize for missing today, but I think that this is a decent alternative for getting you guys, keeping you up to speed as far as getting through the material for the semester. We kind of jumped back and forth a little bit in chapter 10, and this stuff that we're going to be talking about today is in section 10.1 and 10.2, and it's about type 1 errors, type 2 errors, and the power of a hypothesis test. Okay, so what we've done so far in this class is we have we've done a couple of different hypothesis tests, one for means and one for proportions. And we haven't really addressed the idea that once we make a decision, that sometimes that decision that we make is the right decision and sometimes it's the wrong decision. Right, and so I'd like to take a look at the types of errors that we can make, and then also talk about the power of the test, and we'd like the power to be high. The power of the test is the sensitivity of the test in determining to make a correct decision. Okay, so let's take a look at, we're going to make a decision either to reject the null or we're going to fail to reject the null. And either the null hypothesis is true, or I think I want to change this to, instead of saying the null hypothesis is false, let's just say the alternative is true. Okay, so if the null hypothesis is true and we reject it, okay, this is an error. The null hypothesis is true, I don't want to reject it. And not only is this an error, this is a type 1 error. Okay? Now, if the alternative is true, then the correct decision would be to reject the null. So this is a correct decision. Okay? Down here, if the null hypothesis is true and we don't reject it, this is also a correct decision. Okay? But if the alternative is true and we fail to reject the null, then this is also an error, and this is the type 2 error. Okay, now one of the things that we're going to be really kind of interested in is being in this cell here. Okay, if the null hypothesis is, or if the alternative hypothesis is true, we would like to reject the null. Okay, and this part, this is called the power of the test. Okay, the power of the test is the likelihood of making the correct decision to reject the null hypothesis when we should. Okay, so those are the four different outcomes. This one down here we're not ever really all that concerned about. It's just the null hypothesis is true, we fail to reject it. That just means that whatever we suspected wasn't the case, okay, and we made the right decision. So a type 1 error occurs when the null hypothesis is true and the decision is to reject it, okay? So let's say that we're testing to see if a coin is fair, right? And so we're going to flip it a bunch of times. Okay, if the coin is fair, we would expect that the proportion of heads would be 50%. Okay, and then let's say that our alternative is that the coin is not fair. Okay, that the proportion of heads is really bigger than 50%. Okay, it comes up heads more often than it should. Okay, so in this example, a type 1 error would be the null hypothesis is true, we have a fair coin, we flip it, let's say 100 times, and we get a proportion that is high enough. Let's say it was like, I don't know, 65 heads and 35 tails. That's probably high enough to reject the null hypothesis at the 5% level, right? And that would be a mistake. Okay, we just happened to flip the coin and it came up heads more times than it should have. Okay, that would be a type 1 error. Okay, we would say the coin is unfair when in reality it's not. Okay, that's a type 1 error. All right, now if you think about what is the probability of making a type 1 error? All right, well, if the null hypothesis is true and we reject it, remember we're going to reject the null hypothesis if our p-value is small enough. All right, so the probability that we're going to get a p-value that's small enough from a hypothesis that is true is just whatever the alpha level is. Okay, so the probability of a type 1 error is equal to whatever the alpha level you set. Okay? So if you want to be fairly confident that you're not going to make a type 1 error, you probably want to make the alpha level something relatively high. Okay? Sorry, we want to make the alpha level something relatively low. Okay, we want to be in this cell, or we don't want to be in this cell, we want to be in this one. If the null hypothesis is true, we want to fail to reject it. And we'll fail to reject if we make the alpha level smaller. Okay? Then a type 2 error is over here in this cell. Okay? A type 2 error occurs when the null hypothesis is false and we fail to reject it. In our example, what is the probability of failing to reject the null hypothesis when in fact it is false? What does it depend on? Okay, so in this setting with the coin, okay, we're making a type 2 error now, which means that the alternative is true. Okay, the coin is weighted in such a way that it comes up heads more often than it should. Okay, so let's say that it comes up heads more often than it should. Let's say it's set at coming up heads 60% of the time. Okay, now we're flipping a coin that is weighted this way. Okay, and we want to know what is the probability of a type 2 error. Okay, so if we want to find the probability of a type 2 error, we want to find out what is the probability that we're going to fail to reject the null hypothesis when it's actually true. Okay, this might be easier to look at when we talk about power, because power is just the complement of a type 2 error. Okay, it does make a lot more sense to talk about the power. So the power of the test is, if this coin is set so that it comes up heads on average 60% of the time, the power is the probability of rejecting the null hypothesis. Okay, so if we think about what does the power depend upon? Okay, well, one thing that the power is going to depend upon is the alpha level. Okay, if we want to be here, we want to reject the null hypothesis, and in order to reject the null hypothesis, we can increase the alpha level. Okay, so if we get a p-value of, let's say, 7%, if we increase the alpha level to 10%, now all of a sudden we're going to reject the null hypothesis there. Okay, the other thing that we can do is we can increase the sample size. Okay, if we increase the sample size, that's going to give me values that are more clustered around 60% and is probably going to give me reason to reject the null. Okay, I think you're going to see this a little bit clearer when we go through one or two examples. Okay, so I've got one example of using a proportion test. Okay, and this one is very similar to the flipping of a coin. It just happens to be with male and females in a large population. Okay, so a statistician is interested in the proportion of women in a large population. Okay, he's assuming that there's 50% women in the population, and he wants to know, is there evidence to suggest that the proportion is higher than 50%? Okay, and then we're going to say that in reality, okay, this is something we wouldn't necessarily know, but in reality, let's say that the proportion of women is 55%. Okay, he's going to take a sample of 50 people, and we're going to set the alpha level at 5%, and we want to calculate the power of this one proportion z-test. Okay, so calculating the power of this test, we need to look at the sampling distribution of the mean. Okay, now we're really going to have two sampling distributions of the mean here. One of them is going to be based upon this. Okay, so I'm going to call that the hypothesized. Okay, this is the hypothesized sampling distribution of the proportion. Okay, according to our hypothesis, the sampling distribution is going to be approximately normal. Okay, centered at 0.5. And the standard deviation is the square root of PQ divided by N, so it'll be 0.5 times 0.5 divided by 50, and that gives me about 0.071. Okay, Now, we're going to look at this slightly different than we've usually done this because we're actually not going to calculate the p-value here. We're going to talk about the power of the test. Okay, so we're not actually going to take this sample of 50, but what we want to do is we want to come out here to some value that cuts off this top 5%. Okay, so let's say this is 0.05. Okay, so if we get a sample proportion that is anywhere out here, this is what we refer to as the rejection region. Okay, and then I want to know, where is this threshold? Okay, so to find that threshold, we would do inverse normal. Okay, I want to find the 95th percentile. The mean is 0.5, and the standard deviation is 0.071. Okay, so if we get a sample proportion that is 61.7% or more, okay, then our decision is going to be reject the null. Okay, so this is about what we did, except the only difference is we're not actually calculating a sample proportion from this. We're just saying that if we get a sample proportion that is bigger than 61.7%, our p-value is going to be less than 5%. Okay, then I want to look at the reality. Okay, in reality, p is 0.55. Okay, so if I draw another curve, that is centered at 0.55, and the standard deviation of this one is going to be slightly different than the other one because we're going to be using 0.55 in here and 0.45 divided by 50. Okay, this ends up being just about the same, but it's 0.070. Okay, so this is the reality. Okay, this is centered at the true population proportion. All right, and then we want to know, how likely is it that we're going to end up out here in this tail? All right, so now we're looking at the reality is we're selecting from a population that has 55% women. So if we wanted to know what's the likelihood that we're going to be out here above 61.7, we really need to look at this probability. Okay, and calculate what's in that right tail. All right, so the power of this test is going to be a normal CDF. We're going to go from 0.617 to infinity with a mean of 0.55 and a standard deviation of 0.07. Okay, and when I calculate this, I get the power is 17%. Okay, so what does this mean? So this means that if we ran this test, and in reality, the alternative is true, that the proportion of women is really 55%. The likelihood that we're going to make the right decision, that is to reject the null, is only 17%. Okay? If I gave you all an assignment, go out and select 50 people from this population and run this test, that 17% of you would probably reject the null. Okay, which means the rest of you are going to make the wrong decision. So the probability of a type 2 error would be 1 minus 0.17. So there's an 83% chance that you're going to make the wrong decision here. All right, now there's a couple of reasons why that this number is relatively small. One reason is because these two numbers are not that far apart. Okay? There is slightly more than half of the people in this population are women. Okay, another reason why this is fairly small is we probably should have taken a bigger sample size. Okay, if we take a bigger sample size, you can kind of imagine that these graphs are going to be squeezed together a little bit more. There'll be less overlap on the two graphs, and you're going to find the power is going to go up. Okay, I've got another example where I'm going to demonstrate that using GeoGebra. Okay, so three things. these two numbers are not very far apart. Our sample size is not all that big. And then also, our alpha level is at 5%. Now, if you imagine what would happen if we increase this to an alpha level of 10%, well, if I did that, this black area here that I marked as 0.05, I want to make that 10%. So now we're going to be over here someplace, and we'll have a threshold that is a little bit smaller. All right, and then if you think about, well, what's the area underneath the red curve then? It's going to be more. Okay, so we can increase the power by increasing the sample size or increasing the alpha level. Okay, and then as the power increases, the probability of a type 2 error is going to decrease because they're complements of each other. Okay, so let me give you another example. This was an example that was actually, it was on the AP exam a couple years ago. Okay, so for this problem, this is about systolic blood pressure, is the amount of pressure the blood exerts on blood vessels while the heart is beating. The mean systolic blood pressure for people in the United States is reported to be 122 millimeters of mercury. And the standard deviation, we're going to assume that we know that standard deviation is 15. Okay, we should really be doing a t-test on this one, but when we're doing power, we're going to end up using a z-test. Okay, so I hope this doesn't bother you that now we're going back and saying, suppose we know what sigma is. Okay, we kind of need that in this problem. Okay, so the wellness department of a large corporation is investigating whether the mean systolic blood pressure of its employees is greater than the reported national mean. A random sample of 100 people will be selected. The systolic blood pressure of each employee in the sample will be measured and the sample mean will be calculated. Okay, so we're setting up our hypotheses that the average blood pressure for people that work at this company is the national average. Okay, we're trying to see, is there evidence to suggest that it's higher than that? Okay, so first question here is to describe a type 2 error in the context of this hypothesis test. Okay, so if we go back here, the type 2 error is here. It says the alternative is true, okay, which means that these people have high blood pressure on average. Okay, but our test says otherwise. Our test says that they're normal. Okay, so a type 2 error here would be that in reality, these people do have high blood pressure, but our test indicated that the alternative was true. Okay, so now if we assume that alpha, the standard deviation of all employees at the company, is 15, if mu is 122, the sampling distribution of x bar for samples of size 100 is approximately normal with a mean of 122 and a standard deviation of 15. Okay, I'm going to show that to you on a GeoGebra file, and let me hide some of these things. Okay, so the red graph is what we're hypothesizing. Okay, and maybe I can do this so we can see both. Okay, so it says assume that sigma is the standard deviation. If mu is equal to 122, the sampling distribution of x bar for samples of size 100 is approximately normal with a mean of 122 and a standard deviation of 15. What values of the sample mean would represent sufficient evidence to reject the null hypothesis at the 5% level? Okay, so what I want to do is I want to find out where is the threshold out here that cuts off the top 5%. Okay, so to do that, I'm going to go to my calculator. And I'm going to do an inverse normal. I want the 95th percentile for this distribution. And the mean is 122. And the standard deviation of the sampling distribution is going to be 15 divided by the square root of 100. And it tells me that that value is 124.46. Okay, so I'm going to display that here by just turning that part on. Okay, so that red region is the top 5% of the sampling distribution if the null hypothesis is true. Okay, now, in reality, the mean is not, let me go back to the document. Okay, so now it says, the actual mean systolic blood pressure of all employees at this corporation is really 125, not 122. But the standard deviation is still equal to 15. Okay, so now, using the actual mean of 125 from part B, determine the probability that the null hypothesis will be rejected. Okay, so if we go back here to the GeoGebra file, and I turn on this graph is the, no it's not, it's got to be centered at 125. This graph, the blue graph, is the reality. Okay, that's centered at 125 and has a standard deviation that is also equal to 15 divided by the square root of 100. Okay, now we want to know what's the probability that we're going to get a value that's out here in the rejection region. Okay, so we want to calculate what's the probability of being to the right of 124.45 on the blue graph. Right, and so if I find that, it tells me that the power of this test is about 64%. Okay, so the power of this test is 64%. Okay, that just means that if we were to run this test and the null hypothesis is false, that actually people have high blood pressure, okay, the probability that we're going to make the right decision is about 64%. The probability we're going to make the wrong decision is about 36%. Okay, now the last question on this one says, suppose that we increase the sample size. Okay, so let's think about what's going to happen if I increase the sample size. So what will happen to the red graph is it's still going to be centered at 122, but the standard deviation is going to get smaller, and that red graph is going to get taller and skinnier. Okay, the blue graph is going to be centered at 125, and it's going to get taller and skinnier. All right, and I put this on a slider so that I can see what happens. All right, so if I increase the sample size, let's say to like 265, let's go up to about 330. Okay, notice that this red part of the graph, or I guess it's in purple now, is the top 5% of the red graph. And then the probability of actually getting a value that is in that top 5% now is going to be about 98%. All right, so if we did the same test, but we did it with a sample of 330 instead of 100, we would be pretty sure that we're going to reject the null hypothesis. Okay, so if I increase the sample size up to a fairly big number, we can get the power to be, well, it says 1, but it's actually just a little bit less than 1. Okay, so if we took a sample of 760 people instead of 100, we would almost every single time we would reject the null hypothesis. Okay, so let's bump that back down to 100 where we started. Okay, and then let's say we wanted to change the alpha level. So if we change the alpha level from 5%, let's say to 1%, okay, this purple region is going to get smaller. Okay, we're going to be looking at the top 1% instead of the top 5%. So if I do that, you'll notice also that the power is going to go down. Okay, and it goes down just because this line slides over. But if we increase the alpha level, let's say to 10%, okay, with a higher alpha level, we're more likely to reject the null hypothesis, and the power goes up to 79%. Okay, the one thing that we don't have a lot of power over is, or we don't have a lot of control over, is what is the actual mean? Let's say that this actual mean was really like just a little bit above average, like 122.5, let's say. Okay, the null hypothesis is still incorrect. The mean is actually 122.5, but if you notice, the power of this test is really pretty small. Okay, it's only about 10% now. All right, if I bump this up, you'll notice that that blue graph just slides over, And what if they were really unhealthy and had like an average blood pressure of like 129? Okay, if the average blood pressure was actually like 129, then our power would be almost 1 again. Okay, so those are the things that kind of control the power of the test. Okay, now in reality, we are going to be doing t-tests in this context. And so we need a way that we can talk about the power of a t-test. All right, so let me go back to the document camera and we'll take a look at this problem. All right, so this problem is the wellness director is interested in determining if the mean resting heart rate for employees at a large manufacturing plant is greater than 65 beats per minute. His hypotheses are that the mean is 65, his alternative it's more than that. Suppose that in reality the mean heart rate for employees at this company is 70 beats per minute, and he plans to take a simple random sample of 10 people from the company, and he plans to set the alpha level at 5%. Okay, so I'd like to be able to approximate beta, the probability of a type 2 error, and then also find the power of the test. All right, now the problem with this is we're going to get our sample standard deviation, S, from these 10. All right, and I don't know what that number is. Okay, I haven't taken the sample yet. All right, so it makes it really difficult for us to calculate the power using any kind of formulas that we have. All right, so what we do is we calculate another statistic, this D statistic. All right, and I'm going to tell you first of all that this is not as important as some of the other stuff that we're talking about in this chapter. Okay, this D statistic is particular to a one sample t-test. Okay, so what we do is we calculate this D statistic, which is the alternative value minus the hypothesized value. So in our case, the alternative value is really 70. The hypothesized value is 65, so we take 70 minus 65 in the numerator. And then also, we put something in here for sigma. All right, and if you read through here, it says we want to pick like an upper bound on what we think sigma could be. All right, so I'm guessing that maybe these people have some experience with the distribution of heart rates, and they came up with, they think that 6 is a reasonable upper bound on the standard deviation. Okay, that's something that they're probably just going to give you in the problem. Okay, so if I divide these, take 5 divided by 6, I'm going to get 0.8333. Okay, now what we'd like to be able to do is calculate the probability of making a type 2 error, and then from there we want to find out what's the power of the test. Okay, so let's think about this first. The bigger this number is, the further these two numbers are going to be apart, which means that the power is going to be higher when this number is higher. Okay, and if the power is higher, that means that the probability of a type 2 error is lower. Okay, the standard deviation on the bottom, that kind of controls how compressed our graphs are. If this is a big number, we're going to end up with a smaller number over here. So the larger this number is, the smaller this number is going to be, and the higher beta is going to be. Okay, so in order for us to calculate this, we can't really do a normal CDF on this because we have a t-distribution. So in the back of your book, there's a table B in the back of the book, and it's a way that we can calculate the power of a test and the probability of a type 2 error by looking at these graphs. Okay, so up here it said that we had a sample of size 10, which means that our degree of freedom is 9. All right, so if we look at the graph that is 9 degrees of freedom, it's this graph here. Okay, and then we calculated this value of D, which is along the horizontal axis. So 0.833 is about there. Okay, and then if we go up until we hit the graph with 9 degrees of freedom and then come over, we find that beta is about 20%. Okay, so beta in this case, this is the probability of making a type 2 error is 20%, which means the power of the test is going to be 80%. Okay? All right, and if you think about what happens if we were to change some things here, if these two numbers were further apart, then we would end up with a number that's a little bit bigger along this axis. So let's say we go out here to, like, I don't know, 1, and then we do the same thing. we're going to find that beta now is less than 10%. Okay, and if these two numbers are closer together, we're going to get a d that is smaller. So let's say that it was about like 0.6. We go up here on the graph, and now the probability of a type 2 error is 40%. Okay, that should be consistent with what we said before. Okay, now this isn't the only criteria that we have. We could have an alpha level that's different, and we could have a two-tailed test as well. And so in that table B in the back of your book, they give you a couple of different graphs. Okay, so the one that we looked at was this one in the orange, but then using an alpha level of 1%, okay, find beta. All right, so we're doing alpha is 1% with a one-tailed test. The degree of freedom is 9 on this curve here. Our D statistic again was about 0.833. So if I go up, I'm going to hit that graph somewhere around in here. Okay, and I said that was about 60%, maybe a little bit less than 60%. Okay, and so the power of the test is only going to be 40%. Okay, so if this test were two-tailed with an alpha of 0.05, so 0.05 and two-tailed test, again, we go to about where 0.833 is. 9 degrees of freedom is this one. We go up on the graph, and we find that beta is about 30%, okay, which means the power is 70%. And then if we did alpha is 1%, and we've still got 9 degrees of freedom, all right, so now we're talking about this curve here, 0.8 something, and then go up and over, we're going to find that beta is 70%, which means that the power of the test is about 30%. Okay, so we really need these kinds of graphs instead of some kind of a formula to find the power of the test if we're doing a t-test. Okay? All right, the important things that you guys should know is what increases the power. Increasing the power, you increase the alpha level. You can also increase the power of the test by increasing the sample size. Okay, the other thing that you should probably recognize is the consequences of making these kinds of errors. So if we think about this one, suppose we made a type 2 error, what would it mean? Okay, so a type 2 error is the alternative hypothesis is true. Okay, the average blood pressure or average heart rate is greater than 65. Okay, so we should reject the null hypothesis. However, we made the mistake. Okay, we didn't reject it. Okay, so what's the consequence? The consequence there would be these people have high blood pressure on average. Our test did not indicate that. Okay, if this is the wellness director at a company, he's probably interested in doing some kind of a wellness program for the employees. He took their blood pressure or their heart rate. They have a fast heart rate, so maybe they could, bring that down by exercise or diet, things like that. So maybe he wants to put together a program, but the test says there's no reason to do it. Okay, so we're missing out on an opportunity to make these people healthier by introducing a wellness program. All right, when in reality they should have one, but we actually failed to reject. Okay, now what if this was a type 1 error? Type 1 error, this is true. The average heart rate is 65. If we made a mistake or an error, a type 1 error would be to reject that. Okay, these people are perfectly healthy, but the test indicates that they have high heart rates. Okay, so what does that mean then? This wellness director is going to put together some kind of a wellness program for these people that don't really need it. Okay, so it's kind of like it's wasted resources. Okay, all right, so you should be able to kind of, from the context of a problem, say, what is the consequence of making each kind of error? Okay, generally speaking, a type 2 error is a missed opportunity. Okay, we missed an opportunity to introduce a wellness program. Okay, that's typically what happens in a type 2 error. Okay, so I think that should get you through the first part of chapter 10. Again, I apologize for not being in class today, but I think that this video serves the purpose. So you guys should be able to work on those problems that deal with power and type 1 and type 2 errors from the early part of chapter 10. And then I'll be back on Wednesday, and we'll keep moving forward with the next kind of tests that we're going to be looking at. Okay? Have a great day, and I'll see you guys on Wednesday. Bye.